Okay, the next reaction we're going to talk about is dihalogenation. Okay, again, this is an alkene addition reaction. So we'll start with an alkene, and we're going to add X2, all right? That will, again, as every addition reaction, break the pi bond. We're now going to add two X's, two halogens. Okay, because we're adding the same groups, right, we don't have to worry about Markovnikov or anti-Markovnikov, but we do have to worry about the stereochemistry of these groups, and it turns out that the stereochemistry of these are going to be anti, right? So if we look at our reagents, okay, we're going to be adding X2, so that could be Br2, Cl2, I2, CCl4 is our solvent, okay, and we'll see in our next video why the solvent is important. It's okay to leave out the solvent in some examples, but in these two examples I did include it. So if we look at our first example here, right, we have an alkene. We're going to break the pi bond, right, so we just have our sigma bond left, and we're going to add our two bromines to the two sp2 carbons. So we add the two bromines here, okay. Now what you'll notice here is I didn't draw these in anti. You can if you want to, but you actually don't have to. But when they're added, the two bromines have an anti-relationship. And why we don't have to worry about it, as we've seen before, we only have to draw stereochemistry when I've formed two new stereocenters. And in this case, the highlighted carbon is a stereocenter, but this carbon is not, right, because we have two methyl groups here. So we only have to show that the reaction is anti when we have two stereocenters. And that's what we see with our second example. So when we add Cl2, right, we're going to add two chlorines across the double bond. And now we have to show that the chlorines are anti with each other. One has to be a dash and one a wedge. We have a racemic mixture of this, which means we have a 50% mixture of that enantiomer, and then a 50% mixture of the other enantiomer, where the chlorine on the top is back. That pushes this methyl towards you, and then the chlorine at the bottom is coming towards you. All right, so we have a 50-50 mixture of these two, all right? And in my class, when I teach this, you can just draw one or the other. You don't have to draw both, all right? So to kind of figure out why we have anti-addition, what we really want to do is work on the mechanism. So let's review the mechanism here. Let me just clean up this bottom example, and we'll do the mechanism of this reaction, all right? So what I'm going to do is draw out our Cl2 molecule. So we have a chlorine-chlorine sigma bond. Each has 3 lone pairs. And it turns out the bond in between these two chlorines is somewhat weak. Okay. It's a weak bond because the halogens are big, which means it's easy to break. All right, and that's perfect for the pi bond of our alkene. So our pi bond is going to attack, the pi bond will attack the chlorine, and that will then break this chlorine-chlorine bond. Okay, so let's add that chlorine. Let's draw that in blue. Let's add that chlorine here, and then the consequence is when we add the chlorine at the bottom, this carbon on top only has 3 bonds, therefore that carbon has a positive charge, all right? And just remember, we don't have to draw it. There's a hydrogen here, there's still a hydrogen there, right? That's why the carbon at the bottom doesn't have a charge. It's got 4 bonds. What's interesting about this species here is that this chlorine has lone pairs, and we now have a carbon atom that doesn't have a full octet and is missing a bond. So we can draw some resonance structures of this, right, where this lone pair is actually forming a bond to that carbon. So we can draw another alternate structure where the chlorine is in fact attached to both carbons. So it has 2 bonds and 2 lone pairs. That gives us 6 valence electrons, 1 less than it wants to have. So that chlorine can then have a plus. Or in fact, the chlorine can be attached to the other carbon on the top, and then the carbon at the bottom has a positive charge. So there's sort of 3 structures here. Now this is a secondary carbocation that's not as stable as the tertiary carbocation. So sort of these first 2 structures are really most important, all right? And it turns out this intermediate is going to determine why we have anti-addition. So we saw earlier with syn addition, the 2 groups are normally added at the same time. They're added in a concerted mechanism. Now we have an intermediate, and if we kind of highlight on this ring here, right, we have a 3-membered ring with a chlorine. So the next step in the mechanism, right, if you notice here we broke this, that gives us a free Cl-, and that's going to act as our nucleophile. Okay, that's going to act as a nucleophile. Because the chlorine here has a full octet, it is not electrophilic. The chlorine has a full octet, it cannot accept any more bonds. But what can accept bonds, right, is the carbon. So because we have both of these structures going on at once, it's one intermediate represented by 2 different structures. What we can see when we have a 3-membered ring here is this is going to sit on one face of the molecule, right? This is really going to be on the top face of the molecule with the methyl back, or it will sit on the bottom face as such, right? And really what that means is that is blocking either the top face or the bottom face. So when our chlorine comes in and attacks, and I can draw the arrow in my mechanism here, or I can have the chlorine kind of attack here and open up that bond, right? So this is our second attack step. This chlorine has to attack at the opposite side of where that chlorine is, right? And we'll learn a little more about this sort of backside attack or opposite attack. But when this attacks here, it's got to attack on the opposite side, which means we get our product that the 2 chlorines have to be anti, right? So when we do this attack step, it's going to attack from the opposite side, which results in the 2 chlorines being anti to each other, right? So the 2 chlorines are trans. And again, we can kind of draw this where the top chlorine is a wedge and the other's a dash, or vice versa, all right? So we see through the mechanism in the second step why we have an anti relationship in the 2 chlorines or the 2 halogens.